If you're like many other parents, you probably thought that you had a really strong understanding of multiplication until your fourth grader brought home their homework and tried to explain it to you. And you realized that the way that we do multiplication now at school is quite a bit different than the way that we did it when we were in school, however many years ago that might have been. And it may look to parents like we're teaching them all these different strategies when why couldn't they just learn one? I actually don't see the way that we teach multiplication these days to be teaching them a lot of different strategies. I think of it as a way to prepare them to better understand the one strategy that we learned when we were kids. So as you can see on this model here that I created for the class, we actually are starting with something that's really concrete, and we're becoming increasingly abstract as we work our way up to being able to use the formal algorithm that we learned when we were in school. All of the other rungs on the ladder are a way of getting them closer to that algorithmic approach to multiplying, which is, as we know, the most efficient way to actually solve multiplication problems. So what I thought we'd do today is I'd start by explaining some of the different methods to use so that you get a better understanding of what it is that we do and why. Just looking at this model here might not fully prepare you. Hopefully, if you ask your children, they'll be able to give you more explanation, but here's my explanation for you today. So when we're thinking about multiplication and any other math concept, it's really useful. Here we go. It's really useful to be able to think in terms of things as opposed to thinking in terms of just numbers. Things make sense to kids, numbers don't always. So let's start by thinking about groups of 4. Let's say that I have 4 students sitting at a group. I could represent that as a picture of 4 kids, or I could show that as an array. So here I've got one group of 4 students sitting together at a table. I have 4 students altogether. If I put in a second group of 4 students, then I could represent that as a picture, or I could just show it as this array. And finally, if I added a third table or third group of 4 students, then I would add a third row to my array. This array is also known as the area model of multiplication because there is quite a strong connection between multiplication and area. But of course, in grade 4, we're hoping that our students are going to get well beyond this, and we get to the point where we need to represent these concrete ideas, not by counting individual concrete materials, but by working with slightly more abstracted ideas. So we might start by thinking about this idea of a 2-digit times 1-digit multiplication equation. In the first example here, you can see that they've taken this idea of 14 times 6, and they've broken up this 14 into 10 and 4. Where we look on the model, we see that here we've got 6 rows and that there are 14 in each row. Multiplication requires for the mathematicians to break up numbers to make them easier to work with. So here what we're going to do is we're going to break up the 14 into 10 and 4. Of course, we know that 6 times 10 is 60, and 6 times 4 is 24. Then all I need to do is push these 2 parts of our area model together, and I end up with 24 plus 60 equals 84. Now this is kind of a way to build our way up to the algorithm. From there, we could take this idea and represent it not as a closed array like this is, where a student could actually go and they could count to make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At the beginning, when they're just learning this, they may need to go to that concrete a level. But as they become more sophisticated in their thinking, they can actually take that same idea and draw their own open array. So they would show here there's 6 rows, and they would think, okay, well, 14 is quite a bit bigger than 6. So here's my area model. I could think about it like a carpet, or I could think about it like something else, some other concrete thing. And again, I'm going to take this 14 and I'm going to split it into 10 columns, and 4 columns. Why? Because nobody expects anybody to know their 14 times tables, but we do know our 10 times tables and our 4 times tables. 6 times 10 is 60 again. 6 times 4 is 24. So what I've done is I've just used a partial products approach. Partial products means I'm finding the product or the answer to 14 times 6 or 6 times 14 part by part. So 14 times 6 equals 60 plus 24, it equals 84. So this we would call partial products, or finding the product part by part. Now from there, we can become even more abstract, and we can break it up in an even more abstracted way. So again, I can take my 14 times 6, and I can break my 14 up into 10 and 4, but using what we would call the box method. It's just a slightly more abstracted version of what we already did here. Now I'm doing 6 times 10, 60, 6 times 4, 24. And again, I add them together and it gives me a total of 84. To become even more abstracted, eventually students are going to begin to understand that to do 14 times 6, I actually need to find the answer to 10 times 6 and then 4 times 6. And this is actually what we're doing. We're mentally decomposing these the factors. We're decomposing the 14 into factors that are easier to work with. And again, I can solve for each of the elements of this, and it gives me the answer. Finally, we translate that or transition that into the formal algorithm. Again, I'm starting with 6 times 4. We see that up here. 6 times 4 is 24. I can't put 24 in the units place, so I remember that I have 2 extra 10s there. 6 times 10 is this part here. This is where some students get confused. They're not sure what to do with this 2. But we don't have 3 10s, we only have 1 10. These 2 10s come from the item before. 6 times 1 is 6, plus the 2 gives us 8. And that's how students move up the ladder to multiply a 2-digit number times a 1-digit number, where they start with something very concrete and become more abstract until they get to the algorithm. This is the destination. These different levels of abstraction bring them there with understanding.